Well, thank you for coming. My name is Brian Borum. I work for a company called Weaveworks. So let me just check who's in the room. Who had heard of WeaveNet before they read the schedule? About half the room. That's okay. And who identifies as like a kernel developer or a device driver or DPTK developer or? Okay, they've all left. Okay, that's great. So we can. Because I put on this slide, I am not a networking expert. I'm like a programmer, and I've been looking after this project for 5 years. It's been downloaded 250 million times. It's starred 5,000 times. There's certain things to be proud of, but. It's fundamentally, I don't think I did anything clever. So I'm kind of glad that all the clever people have left the room. And I put my smiling face up somewhat because I'm going to put a bunch of people up. This is a talk somewhat about the technology and somewhat about the people and the history of this project. So hopefully that's interesting. So what is WeaveNet? It's a container network, and I'll talk about that in a minute. The primary thing we were aiming for is that it's easy to install. It just works. It runs anywhere, and there's a little asterisk because we mean anywhere that is Linux. But Windows runs Linux now. We have tried this. You can actually run WeaveNet on WSL. So nearly everywhere. So, and we never, it's open source, it's Apache licensed. We never made an enterprise version. So enjoy. Yeah, what is a container network? Well, we had one definition from Justin Garrison, works for Disney. I'm an admirer of his work and generally the work of Disney. It's good stuff. But he said there's no such thing as container networking. So that was a bummer because I've been working on it for 5 years. But actually, it turns out he uses WeaveNet and it just works. So yes. So more seriously, what is a container network? So the point of containers is or one point at least, is isolation. That through namespaces and kernel features, one thing is sort of believes it's completely separate from another thing, including network. They have separate network namespaces. So now, how do these things talk to each other? Well, whatever the answer to that question is, that's a container network. That's the definition I'm going to work with. Okay, let's go back. Okay, let's go here. Conceptually, what does this mean? So I'm going to put up a large number of diagrams that look a little bit like this. So the meaning of the shapes, the big darker blue shape is a machine, whether it's bare metal or VM or something like that. That's your kind of node in the network machine, and the light blue blobs are containers. Okay. So sometimes containers are talking to each other on the same machine. Sometimes they're talking to each other on different machines. And by and large, we're going to have like lots of these things. And they're all going to be talking at once in different amounts. Okay, so that's the kind of theoretical high-level model that that's what we want to do. Let's go back 5 years, 5.5 years. This smiling face, Mr. Sackman, wrote the first version of what became WeaveNet. He was out of RabbitMQ. In fact, the founders of Weaveworks all came from RabbitMQ. So he's an Erlang programmer. And the code a lot of the code has quite a strong, it's all written in Go, but it's a strong kind of Erlang flavor to it, which is kind of cool if you want to think about that. 3,400 lines was the first commit. Spoiler, we're at like 30,000 lines now, so it's growed a bit. Anyway, so basically what we do at that version, fundamentally what we do is we put a bridge, a Linux bridge on each machine. We connect all the containers on one machine to the bridge, and then we tunnel the packets from one bridge to another bridge. So that's the kind of the conceptual model taken to an actual implementation. Let's take that down a layer further. So specifically, we set up a bridge. For each container, we set up a VETH, virtual Ethernet device. One end is inside the container namespace. One side is attached to the bridge in the host. And we listen on that bridge using PCAP. Whoa. The room went quiet. No, seriously, we tested 3 different ways to do it, like tap devices and whatever. And as at 5 years ago in Go, as it stood, PCAP worked best. So, so there it is. So if you've got 2 containers on the same host, they're both attached to the same bridge. They'll just talk to each other over the bridge, and WeaveNet doesn't get involved. If you have 2 containers on different machines, then we're going to pick up those packets. We're going to put them in another UDP packet. It's kind of homegrown encapsulation, and we're going to send that over the network and deliver it to the bridge, again via PCAP, packet injection on the other side, deliver it to the bridge, and that's going to end up at its destination. This is, I like to call it at least, a distributed Ethernet switch. It is, WeaveNet implements an Ethernet switch. It's a layer 2 network. It works purely in terms of MAC addresses. It does what a dumb Ethernet switch does. It learns MAC addresses by seeing a packet come in, and it observes the source address that it came from. And when later on it has a packet to send to that destination, it uses what it learned, and it delivers the packets that way. So a physical Ethernet switch is going to deliver on different cables. Where in software, we're going to send to different hosts. But it's exactly the same concept. And we also have the same fallback behavior. If we don't know where it's supposed to go, send it everywhere. That behavior will come in useful later. This is a real website. Somebody was kind, I didn't put their smiling face up. Somebody was kind enough to make this website, pointing out something that we did actually know. But if I step back, can I step back? Yeah, okay. So yeah, the reason it's kind of slow is we start off in user space here in the program that's trying to get some work done. We go down into the kernel here. We go back up into user space through PCAP. We put it in a UDP packet. We go down into the kernel again, across the physical network, and then do the same thing again. We go like up, down, up, down, up, down, up, down. And yeah, it's kind of slow. It's terribly slow. It adds. We used to measure it, like 5 years ago, we used to measure it at 300 microseconds per packet extra latency. Now, you have to set this aside. What are you actually going to do with those packets? If the next thing that happens is they get delivered to a massive heap of PHP code, then 300 microseconds is not your problem. But whatever. Yeah, it's kind of slow. Okay. So next step in the evaluation, we implemented what we call the fast data path, because we have no imagination when thinking of names. So kind of similar picture. The packet starts off in a container. Again, we've attached a VETH. The other end of the VETH now is in a different device, which is a vSwitch data path. So this is implemented by a kernel module from the Open vSwitch project. This is the only piece of the Open vSwitch project that we use. So we're in these daemon processes are basically implementing our control plane independently of Open vSwitch, but we're using their kernel module. So it takes the place of the bridge, at least in this version of the code, and we add a few kind of bridge-like behaviors to it to get everything we need out of it. But once a source destination MAC pair has been seen to be talking on the container network, we set up a VXLAN tunnel, and that goes kernel to kernel. So the packets don't do this up, down, up, down, up, down thing. They are encapsulated, which costs you a little bit. But we used to measure this like on a 10 gigabit network, which we thought was fast in 2015. On a 10 gigabit network, we'd measure 8 gigabits of throughput. So it wasn't that bad. It's doing encapsulation, but it's kernel to kernel, and it's delivered to its destination pretty fast. So the person that did this was Mr. Rag, Dr. Rag, I should say. Almost everybody that worked on WeaveNet has a PhD except me. Sorry. Yeah, so like I say, I like to put up the smiling faces. So that's the fast data path. Fixed our main kind of obstacle that we had in the marketplace, which was that it was kind of slow. Let's talk a bit about how we set all these things up. So, right from the very beginning, we need a bridge, we need vETHs, we need to step into network namespaces, step out again, we need to set up some IP tables rules, we need to set up some sysctls, a bunch of things we need to do. So, how do we do all that? In a shell script. We borrowed liberally from this project called Pipework by Jerome Petazzoni, who was at Docker at the time, I think. And this project is a shell script. It turns out it's actually really concise to do the kind of IP, NetNS, blah 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 stuff. So we had our own shell script, which is called Weave, and it started off 350 lines, and it has these commands like weave launch and weave attach and so on. At peak, it got up to 2,500 lines. It's not a very nice place to be to maintain a 2,500 line shell script. So I sat down and re-implemented a lot of it into Go. So it's currently, I mean, this is the latest commit. It's at 1,600 lines or so. It's the features keep getting bigger, and the option it works in all kinds of different modes and so on. So that bloats it. But one thing is when recoding from these things in shell script to Go, the code gets like 50 times bigger because Go is notoriously verbose. But there we are. So what else? We do encryption. We do that both ways with the fast data path and the slow data path. We renamed Sleeve because slow data path didn't seem like a good branding position corporately. Sleeve is a thing that encapsulates some. I don't know. Anyway, so cunning metaphor here. In user space, we use the NaCl library. NaCl, sodium chloride, salt. Yeah, okay. To do our encryption. In kernel space, we use the XFRM framework, and there's a wonderful explanation on that link at the bottom, all the minute details of how we do this. One interesting tweak, we couldn't get this to work at all for months. essentially because the Open vSwitch data path doesn't provide any way to drive the packets through the XFRM framework. We can't set a policy to say everything on this data path go through here. And eventually, the idea how to fix this we stole from Docker. We put all the packets through an IP tables rule which marks them, and then set a policy on that mark. So we have an IP tables rule whose only function is to glue these two bits of software together that otherwise, inside the kernel, that otherwise don't play. And that's kind of a lot of the history of this project has been sort of fighting with things that didn't quite want to do what we wanted them to do. That's the history is there in the code, and some of it I can remember. But anyway, so we encrypt the packets. We're doing key management up here. We did not roll our own crypto, and yeah, some people like that feature. It's encrypted on this side. It's encrypted when it hits the underlying network. It's not encrypted here. So if you've managed to get onto the machine and you can sniff this VETH, then you'll see the plain traffic there. But I always reckon if you've got that much access to be on the machine and sniffing a VETH, then you probably lost the game already. So who knows? What else? Oh yeah, Martinez wrote this. Martinez did all the gluing things together at the XFRM level. He now works on Cilium at Isovalent, which is that vendor. So that's Martinez. Okay, so change tack again. WeaveNet is a peer-to-peer network. Well, the title of this talk is like no central point of control, and it's a pun on the management style and the technology. We wanted it to just be install and run, whether you're running it on your laptop or in the cloud or on 100 hosts or whatever. What most people did to put together a container network was they rely on something like etcd to be a central, consistent store of what's going on, to hold all the container information, all the routes, all the whatever. And we didn't do that. So WeaveNet is completely peer-to-peer. You can start with one peer and you can start adding more peers. They talk to each other via gossip. So I've given each one a little flag. Each peer has an identity on the network, and that peer can be present on the network, or it can go away. You can close your laptop and take it on a plane and open it up again, and it'll still work on the network. So the way we do that is all the shared data structures are implemented as CRDTs, as eventual consistency data structures. They're specially designed so that we can do that. Like somebody can be absent for any number of hours and come back again, and the data reconciles. It all fits together. That is incredibly hard work. So anyway, it has this property that you don't have to set up etcd before you get started, but it is very hard work. We do this for IP address management as well. We do it for several things, but one of them. So we basically take an IP address space and map it onto a ring data, like a distributed hash table type ring, that idea, and then spread that across the network, and gossip updates to that ring. That's how we do IP address management. Yeah. Okay, I wanted to talk about the community a little bit. So as I think I have a chart here. So this is the well, it says installs. This is what we get a count from Docker of the Docker pull operations. So it's running well over 1 million. Yeah, so I mean, it was up at 2 million. This is the 1 year, the last year. 2 million a week, down to about 1.5 million a week. We see this software fire up a lot. We don't, as an open source project, we don't have a very good idea of who's using it, right? We don't. People write in when they have a problem sometimes, but they generally don't tell us just that they're using it and they're happy with it. So this is one of the few bits of evidence we have. The thing gets fired up in some sense 1 million or 2 times a week. Compared to that, we get very few PRs. We get lots of people coming along and saying things like, this is just one I picked on because it came up recently. And this is over a period of 1.5 years, people complaining about a setting and saying, why don't you change the default? It's one line, send a PR. People don't know how, maybe, yeah. So most of the work is being done by people being paid by Weaveworks. This is the GitHub contributors list. Fun statistic, after being the lead on this project for 5 years, I'm the second highest contributor. Matthias Radestock, who is also ex-RabbitMQ, he was co-founder of Weaveworks. He's still the #1 contributor. But all these people work for Weaveworks. This is the Mike Bryant is the biggest contributor who doesn't work for Weaveworks. We do have a kind of long tail of people who did manage to come up with 1 or 2 PRs, which is great, and I would like to encourage that. But it is a little bit dispiriting when people just want to kind of complain about the software and demand that it does something else. Okay, Kubernetes. This is what you were promised, right? This is the theme of this day. So WeaveNet is quite popular with Kubernetes. I thought I'd just kind of run through what does that mean exactly, and what is it doing there, and how does it work. Kubernetes, it doesn't just talk about containers, it talks about pods. A pod is a collection of containers on the same machine. And so in Kubernetes world, conceptually, the blue blobs are pods, but the same stuff is going on. They're talking to each other. And Kubernetes has a very small set of rules, one of which is that any pod can talk to any other pod without going through NAT. Funnily enough, the rules, the sort of model, the networking model of Kubernetes matches very well to Google's network. So I don't know if we'll ever figure out how that happened. But if you run it GK, Google's commercial Kubernetes, then this thing with the bridges, they just have roots like IP root, layer 3 routes from machine to machine. So they have the same thing with the bridges, but they don't have anything else other than the Google network to transmit packets between machines. They just use Linux routing and let the underlying network deliver the packets to a bridge at the other side, and that just works if you're Google. It pretty much doesn't just work anywhere else. So there is a need for something to take that place, and WeaveNet is one of the things that people sometimes choose to take that place. So back around the time this was getting popular, which is about 4 years ago now, the project Rocket, which came out of CoreOS, which was kind of a competitor to Docker, they had this very simple model for network interfaces where they would exec a process that would add a network interface. So that became CNI. Essentially, some people, including Weave workers, got in a room and said, "Yeah, that should work," and it got named and it got turned into a project. And I'm a maintainer of the CNI project, but the CNI is supposed to be really, really thin. I just thought I'd walk through what exactly that is. So CNI is not coupled to Kubernetes. It is, like I said, it came from Rocket. It's completely independent of network and what we call a runtime. So Kubernetes is in the place of a thing we call the runtime in CNI speak. And physically, it's the bit of Kubernetes called the kubelet, which is the bit that runs on each node. So the kubelet calls a CNI plugin. And it calls it, right now, the interface is exec. It execs a process in the host namespace, not in a container. It supplies a JSON config, which lists a few things out, like maybe which subnet you're supposed to be using, something like that. The plugin then talks, I mean, conceptually, you've got a network. Somebody showed up with a network. You bought one from Juniper, or you installed WeaveNet, or you're using Cilium, or whatever. Somebody's got a network. So the job of the plugin is just to be that little bit of glue in between, to interpret this JSON spec and to cause the network to attach itself to a container. So that's the idea of the CNI project, and I think it's worked fairly well in its goal of being agnostic and kind of staying out of the way of people. I do quite often hear complaints that CNI doesn't do this and CNI doesn't do that, and the unfortunate news is it's never going to do those things because it's trying to be the thinnest possible layer that could work for everybody. This is JSON. If you want to say extra things in JSON, just add them. Just like party on. Just add fields. Okay, that's CNI. How do we get WeaveNet installed? So I just mentioned the plugin runs in the host as a process on the host. And everything we're talking about is containers, which are isolated. So we get around that by devious trickery. We mount a directory off the host, and when WeaveNet starts up, it copies the file into the host directory. So now it's in the host. As far as I know, I invented this trick, but everyone does this now. So maybe I copied it from someone else. Tell me at the end if it was your idea. Yeah, so Kubernetes has this concept of a daemon set, which basically means run the same thing on every node, and restart it if it dies, that kind of thing. So that's how we fire up. We arrange for someone to ask for that daemon set. That fires up a copy of our software on every node. We do this trick with copying a file onto the host, and now we're away. So kubelet is now going to call the plugin. Plugin's going to call back up into the daemon, and that's how that all works. I observed about not having any kind of central, consistent idea of what's going on, and of course in Kubernetes you have exactly that. You have the central, what's called the API server, does know everything that's going on in a Kubernetes cluster. And so a few times we thought about abandoning the eventually consistent stuff and just rely on what Kubernetes is telling us, which is what everyone else does. And never quite got around to doing that. Anyway, it's an idea. If you want to submit a PR, that'd be great. We implement Kubernetes network policy, which was mentioned if you were in a couple of the previous talks. So like saying who's allowed to talk to who. We do that by relying on what Kubernetes tells us, because it's the only thing that knows all the labels on different things. And somewhat excitingly, the network is implemented at layer 2, and the network policy is implemented at layer 3. And they essentially have no connection between them. We just run them as two separate processes in the same pod. Anywho, is that all I wanted to say? Yeah, I'll just skip over that. Yeah, that's pretty much what I wanted to say. Does anyone have any questions? Yes.
I used Weave before, so I'm gonna say it's super simple, but I changed from Weave at some point because it doesn't support IPv6.
Okay, so well, that's not a question; that's an observation. But the observation was that Oh, okay. Do we have any plans to support IPv6? So WeaveNet has no support for IPv6 in two ways. It doesn't support IPv6 inside the overlay, and it doesn't support IPv6 as a target on the underlying network. So which of those two did you want? You wanted both of them. And may I ask a question? I mean, the whole point of overlay networks generally is that you have some problem that stops you just routing across from one container to another. And that problem is very often an addressing problem in IPv4. So do you know what problem in IPv6 you're solving by having why can't you just route between the two containers?
Well, if you have some pods that you need to expose them directly outside your cluster. So you need them to be directly exposed.
Okay. So you said your point was that you need some pods.
Globally reachable IPv6 for the pod. You cannot rely on IPv4 addresses.
Now, my suggestion is that all pods can have globally reachable IPv6 addresses.
Yeah.
So you don't need anything else. You don't need me to write any code, because IPv6 will solve your problem.
Well, not all the use cases. For some use cases, you will need some pods to be globally exposed.
All right. Well, I think we'll have to take that offline. Yeah. I mean, bottom line. Nobody did. Why doesn't it support IPv6? Because nobody did the work. It's an open source project. WeaveWorks as a company found something much more exciting to do, which is called GitOps, and you should all buy that. We never managed to monetize WeaveNet. We never made an enterprise version, and we never found anyone that was, for instance, willing to pay us enough money to do an IPv6 implementation. Well, thank you for the question. Any more? One over here.
Yeah. What was that contract race condition stuff?
Question is, what was the contract race condition? So I should put Martinez's smiling face up. Oh, I'm pressing on the wrong button to put Martinez up. So in particular, that link at the bottom is not the right one to look for. I should have changed that, sorry. Okay, I'm just trying to see if I can give you a short explanation of this. Basically, it shows up when doing DNS requests, particularly on Kubernetes, particularly using the muzzle C library. And what happens is it does two requests at exactly the same time for the A record and the 4A record, notwithstanding the fact that we don't support IPv6. The two DNS requests go out from the same source address to the same destination address, same source port, same destination port, and they hit a race condition in contract, and one of them gets dropped.
It's fixed in Weave or
No, it's fixed in the Linux kernel. Yeah, like I say, we spent most of our time not on our own software. We spent most of our time fighting other people's software, including Linux, and in some cases fixing it. So Martinez wrote two patches. He found three race conditions. He wrote two patches to fix two of the race conditions. So this is you can Google like why do I see a mysterious 5-second delay in my Kubernetes
Yeah, I've seen it.
system?
That's why I'm asking.
So this is not the only reason why people see mysterious 5-second delays, but it's certainly a very popular one. The nature of the requests, they are from the same source address, same destination address, same source port, same destination port, and contract does not know how to deal with that.
Okay, thank you.
Yeah. Well, time's up. Thank you.